Okay, now let's take in observation of a traffic from a macroscopic perspective. So the first thing that I define is what's called as an observation window. And it's a window because it's two-dimensional. The first dimension is where I talk about the space, and the second one is where I talk about the time. So let's name the axis space and time. Now this is the actual road over here. So it's a simple scenario where I've got just one road, or rather just one lane. So the vehicles go like this around over here, and this is my coordinate axis system. So I'm probably sitting somewhere around over here, and I'm just looking at this traffic. So in terms of space, this is what the road is. I don't observe anything before this line or anything after this line. So this is the road from the space perspective, and this is the road from the time perspective. So let's say that I start observing from 10 a.m. to 10:05 a.m. So that's a 5-minute window around over here. So let's just take in any vehicle around over here, which is, say, this vehicle, and it's currently 10 a.m. when I start observing it up. So I want to denote this vehicle in this graph. So let's take the characteristic point as the rear wheel axis. So this will be taken as a characteristic point. It's at some distance over here, or it's at time. I'm currently at 10 a.m. Now what happens as it becomes 10 a.m. 36 seconds, 42 seconds, so the vehicle will move. It'll show motion around over here, it'll go here. Of course, it'll be slow because there's another vehicle over here, so it slowly move here. So along with time, there'll be a motion along with the space as well, or this is what the motion is, let's say, expected to be. So that's this vehicle. As it's traveling here, it's of course traveling in the space axis, but then as it's traveling in the space axis, if you look at the watch, the time is also increasing. And I've only plotted it up for this over here. So at any general point, if you want to visualize the vehicle, let this be the length L. So the vehicle is here at this length L in the observation window, and similarly for all others. So there are some vehicles. So like this vehicle was already there when I started observing. There are some vehicles which weren't there when I started observing. However, after a few seconds or a few minutes, they came in and this was there. So similarly, there were some vehicles which exited before my observation time, so I couldn't observe them any further. There are some vehicles which did not exit, which were still there, but I'm a government employee. I say, time's up. I will no longer observe. So these are the ones. So if you want to observe this vehicle, of course it's length L at the space axis. So the actual vehicle is this occupancy, length L. So this axis is space, so I can clearly denote that up. So that's this vehicle. Now this is what's called as a space gap between two vehicles. And this over here at any general point of time, let's say over here, is denoted by this as the space gap. So normally you will expect a very high speed because the space gap is very large when the person in front of you is actually after a very long distance. When the person in front of you is actually after a very long distance, you tend to drive faster. Of course, a derivative of space with respect to time is what is the speed. That is also something that can be calculated around from here. So, and similarly, I can say that the distance between them is 3 meters. So, 3 meter is what is the space gap. I can also say that if this vehicle, it just stops, suddenly stops. I'm not sure how will a vehicle suddenly stop. So, we haven't discussed the speed of the vehicle in front. So let's say the sudden vehicle, I mean the front vehicle, it suddenly absolutely stops, it does nothing. So I say that space gap is 3 meter, but I also say that there's a time gap. So the time gap is the time to collide with the front vehicle if the front vehicle suddenly stops. So that's the front vehicle, and what really happens around is that I say that the front vehicle, it will suddenly stop at a point of time. So at a point of time, let's say that the front vehicle absolutely suddenly stops, and because the front vehicle suddenly stops, this is the one that stays over here itself. And what really happens is that I go along with the time axis, so I go around over here, this is my trajectory, I go around over here, and after some time I'll be at exactly the same space where the front vehicle is. So this is the front of my, this is the rear of my vehicle, this is the front of my vehicle, so this one turns out to be the time gap. So the space gap and the time gap. Normally I would have taken the x-axis as the time and the y as the space, but then I did that intentionally so that I could have drawn the road like this around over here. So the same information which is called as a gap can be defined both in terms of space and time. So in terms of space, it is how much do you see the distance from the front bonnet of your vehicle to the rear bonnet of the front vehicle. That's a space gap. The time gap very similarly is that if the front vehicle just stops, what's the time that it'll take for you to collide? So typically you would expect keeping a 4-meter distance, not in India of course, from the front vehicle, so the space gap will be 4 meters. The time gap you will assume is 3 seconds, of course not in India, so if you continue to travel at the same speed after 3 seconds and the vehicle in front, it suddenly stops in finite acceleration, you expect 3 seconds after which collision is reached. That is what is called as a time gap, and it's all observed within this specific observation window. So I can only see which things which are within this specific observation window. Now let's see is that I define 3 macroscopic variables. So I define 3 macroscopic variables. The first macroscopic variable is what is called as a flow, and it is defined as, in this observation window, the number of vehicles that pass a space per unit time. So I'm over here, this is me, I'm observing, I count the vehicles 1, 2, 3, 4, 5, and then I say how many vehicles pass through this thing. So the formula is of course the number of vehicles that pass this region. I'm counting vehicles 1, 2, 3, 4, 5. So I count the vehicles and then I divide it by time. So number of vehicles per unit time. So the number of vehicles that pass a specific space per unit time, of course you can observe it for the entire space and take the average. So it's number of vehicles that pass per unit time. That's called as a flow. And this is what's different from the microscopic variable. So if I had to model this thing in a microscopic sense, I would have said this is the position of the vehicle, this is the orientation of the vehicle. Of course, currently orientation can only be zeroed, all vehicles travel straight. Now I'm talking about a macroscopic variable, like say what's the flow, how many vehicles per unit time they go. So that's one my first microscopic variable that I use. Now if number of vehicles, I'm defined it in per unit time, I can also define the same thing in terms of the space. And if I define the same quantity in terms of space, it's called as a density. So flow is defined as Q and density is defined as K. That is defined as the number of vehicles that are at any time per unit space. So flow is number of vehicles per unit time, density is number of units per vehicle per space. So now what I do is that I look at everything up, and at any given time I say time pause. So I'm good. I just pause time and I count number of vehicles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by what's the length of the road that I'm observing, 5 meter. So it's number of vehicles per unit space, 5 meter. So the flow is vehicles per unit time that pass through at a. So I mean there are three variables: space, time, and number of vehicles. So if you if you want to study the effects of two, you'll have to keep the third as constant. So flow is number of vehicles per unit time for a constant space, and density is number of vehicles per unit space for a constant time. And the third and the last macroscopic variable that I define over here is speed, and speed would become microscopic, speed of this vehicle, speed of that vehicle. So I define as the average speed. So what's the average speed that I am traveling at? So again, that's something that can be defined both in terms of space average or time average, and the quantities are different. So either I say time pause, I note all the vehicles, what speed they are moving, and I take the average. So this vehicle is moving at this speed, this vehicle is moving at that speed, this vehicle is moving at that speed. Time is constant, time paused. So that's the time average speed. Or I can do it in terms of a space. So I'm at a particular point, I see vehicles pass by, and I keep on noting down at what speed are they moving. So that's the same like speed cameras. They're at a particular space, they just see at what speed are the vehicles moving. And finally you just say that average number of vehicles. The unit in both cases will be meter per second, SI units. In India we use kilometer per hour. Somewhere else we use miles per hour. SI units will still be meter per second. The space average and time average will be two absolutely different quantities. And here we say that it's time averaged. So I've got three macroscopic variables, and now what I will do is the average speed is of course called as V. There's a relationship between them, and that's called as the fundamental equation. And the fundamental equation, it says that the traffic flow is equal to density times the average speed, or flow is equal to density times average speed. The units actually match, so the flow is vehicles per unit time, the density is vehicles per unit space, and the average speed is meter per second. So meter count, vehicles per second. So obviously the units absolutely match. Now that's one thing which I like about transportation, is the use of the term fundamental. So everything is fundamental in transportation. Of course, we are studying more macroscopic variables, we're going more into the fundamental sciences. So that's a fundamental equation of the transportation system, that the flow will always be density times the average speed. Now, if I've got this fundamental equation, so now I've got constraints that limit my three macroscopic variable, or it's not three separate macroscopic variables. I can fix the two and the third one will be derived.